Hey, welcome back. This is derivatives of inverse functions. So we'll begin with some simple facts. Okay, so derivatives of inverses. And these are, I believe, from a theorem. So theorem in the book, I think it's 3.16. I could be wrong though, so I'm just going to put theorem. Let f be a function whose domain is an interval, we'll say I, if f has an inverse, then the following are true. Okay, let me make this look a little better. Okay, first off, if f is continuous on its domain, then so is f inverse. So if f is continuous, then so is f inverse. And geometrically, you could tell this. Maybe there's some more complicated way of proving it. I'm sure there is, but at least geometrically, I think we can stomach the idea that this will be true. So if you think about f as some sort of, I don't know, some sort of function that has an inverse, and maybe it looks like this. To get the graph of its inverse, what do? Well, you just rotate it about the line y equals x, right? And doing this rotation, you would not expect there to be any holes, right? It's like if the original f doesn't have any holes, and to create f inverse, all you have to do is rotate it about the line y equals x, then you wouldn't expect somehow a hole to magically appear in f inverse. Okay, so again, what am I saying? I'm saying that geometrically, from our knowledge of how to produce the graph of f inverse but via this rotation, there should not be any holes produced. Okay? You should be able to still draw the picture without picking up your pen, right? Okay. The second factoid is that if f is differentiable on this interval containing c and let's say on this interval containing c and f prime of c is not equal to 0, then f inverse is differentiable at this point. At f of c. Okay. Again, geometrically, this is kind of obvious. If you think about the derivative as an indicator of the slope of the tangent line to the curve, and okay, let's draw our. I don't want to draw it too crazy because I don't want to. We'll just make it e to the x, right? Okay. So this thing. What that is saying is that so long as it doesn't have a slope that's horizontal, basically, as long as f prime of c is not equal to 0, in other words, the slope at a particular point is not 0, then you'll be able to find the slope on the inverse. Okay, so for example, right here, maybe the slope is kind of positive, and then the inverse function, of course, the logarithm, you can see at that corresponding point on the other side here, it too will have a tangent line with a slope. So it goes to reason that you're going to be able to find the derivative at that point. The only issue may be is if you had something with a horizontal maybe tangent. So maybe like right here, there's some horizontal tangent type deal. And then the problem is when you do this rotation about the line y equals x, well, you tell me what's the problem, right? Well, the problem is you'll get a vertical tangent line, right? So maybe I can draw this thing. I'll try to. Oh, gosh. Okay, so right? And then at this point here, it's going to kind of have a vertical tangent because the other slope was 0. And what's the slope at a point like that? Well, it's undefined, right? It'll have the limit of the difference quotient will be infinity. So the derivative won't exist there. So long as you don't have that scenario, it's differentiable. Okay, so hopefully that kind of gives you some geometric intuition about what's going on. Once you stomach that, then you get this other theorem in the book, which actually gives you a formula for that derivative. Okay, so this other theorem then, and it might be theorem 3.17, but what does it say? It says, let f be a function that is differentiable on an interval. If f has an inverse function, we'll call it g, then g is differentiable at any x for which f prime of g of x is not 0. Okay, it's basically just what that above theorem was saying. But on top of everything else here, we actually have a formula. Moreover, the derivative of the inverse function will be 1 all over f prime of g of x. Okay, so how do we kind of prove that? We can use implicit differentiation, I believe, to kind of get the job done. Consider the cancellation equations. So we recall that if we compose two inverse functions, so I'm supposing that g is the inverse of f, and I'm supposing all the differentiability stuff is intact. So consider the cancellations, in particular f of g of x. We know it's going to equal x, right? And then we can take the derivative of this thing implicitly. This will be f prime of g of x times the derivative of the stuff inside, so that's g prime of x, whatever that is. And then on the right-hand side, the derivative of x is just 1. Okay? And then we could solve for the derivative of the inverse g. So g prime of x will equal 1 all over f prime of g of x. Okay, so there it is. Let's take a look at maybe a type of exercise you're up against. So here they want you to verify f has an inverse, and then use the information to find f inverse prime of a. Okay, so this problem, in this problem, the function given is a cubic. And the value we care about is a equals 2. So first, is this invertible? And if you look at the graph, it's always increasing on its domain. When it's increasing, always increasing, it will pass the horizontal line test. So if looking at the graph, I'm not going to draw it, but looking at graph a nutude, it passes the horizontal line test, and is therefore invertible. Okay, so it's invertible, and so we can then find f inverse prime of A, even though we don't know what the heck the inverse is, right? That's the magic of this. Right, so that's part number one. Number two, we need to find f inverse prime of 2, even though I don't know. I mean, you could try to pause the video and see if you can figure out what the inverse of that thing is. It's just like, no, we can't do it. So anyways, from the above formula, so from above, we know that f inverse prime of 2 will be equal to 1 all over f prime of f inverse of 2. Okay, so we're going to need to figure out f prime, and we also need to figure out f inverse of 2. Okay, so for f prime is easy to get. If f of x equals x cubed plus 2x minus 1, then f prime of x is going to equal 3x squared plus 2. That's just taking the derivative, right? So I have like these two intermediate steps here. For f inverse of 2, I note kind of the relationship between f inverse and f. If f inverse of 2 equals, let's say, I don't know, x, then f of x equals 2. We want to figure out what this x is, because basically we have to figure out what I'm boxing in blue in our formula. I need to figure out f inverse of 2 to plug it into f prime of x. I'll be plugging that thing into there. So I need to figure out f inverse of 2. How do I figure out f inverse of 2? Well, I note that if f inverse of 2 equals x, then f of x equals 2. And then I could solve this equation. So what is the equation I'm going to solve? Well, you just plug 2 in for f of x into the equation for f of x. So 2 equals x cubed plus 2x minus 1, and then solve for x, and that will give us kind of our answer. So you could just guess. One. So I have 2 equals 1 cubed plus 2 times 1 is 2 minus 1. In other words, 2 equals, well, that failed miserably. No, it didn't. That's great. That works, right? So 1 cubed is 1 plus 2 minus 1 is 2. 2 equals 2. So it is x equals 1. So f inverse then, if f of 1 equals 2, so hence we have f of 1 equaling 2, and thus f inverse of 2 must equal 1, okay, which is what we were after. We were after that f inverse of 2 right here. Great. So finally then, there goes my voice. After all this kind of pedaling around, thus f inverse prime of 2 must be equal to 1 all over 3 of, what did we say? This thing was times 1 squared plus 2, which equals 1 all over 5. Okay, okay, great. So interesting, right? Interesting. Let's look at the derivatives of inverse trig functions. So I kind of introduced that in the last section. let's make it a little more formal now. So derivatives of trig functions, and you know, just remember for tan inverse, I'm going to work with tan inverse. We restrict it its range to negative pi over 2 to the pi over 2, right? So to make tangent invertible, I have to restrict its domain from negative pi over 2 to the pi over 2. So this is y equals tan of x. Okay, so tan inverse, what does it look like? It looks like this. And now it has, so this is y equals tan inverse of x. And its domain is from negative infinity to infinity, but its range is that negative pi over 2 to the pi over 2 again. Okay, so great. Well, let's figure out its derivative. Find derivative of y equals tan inverse of x. Okay, so what? Note then, if y equals tan inverse of x, then x must equal tan inverse of y. And once we get that, we can use implicit differentiation on this thing, right? So the derivative on the left of x is 1, and then on the right, the derivative of this thing, whoops, I screwed that up. If y equals tan inverse of x, then x equals tan of y. Sorry. Okay, so if I take the derivative of x, I get 1. Then the derivative of tan of y will be secant squared y times y prime. Okay, sorry. Then I can solve for y prime, which will be 1 all over secant squared y. Okay. Then I can replace secant squared y. Right? You could use those Pythagorean identities. You could think in terms of the triangle. Okay. So this is theta, and we had tan inverse of x. So x over 1 is equal to opposite over adjacent. So opposite is x, adjacent is 1, and the Pythagorean theorem will give us the third side is x squared plus 1 squared, or x squared plus 1. So the secant of this angle here, which is really the angle y, I don't know why I put theta there, I'm used to putting theta there. So it's really this angle y. The secant of that is, well, what is secant again? So secant is 1 over cosine, so it's going to be hypotenuse over adjacent. Okay, so this is going to be equal to then 1 all over hypotenuse, x squared plus 1, all over adjacent, which is just 1, so I could just write it like this. Okay, so it turns out the derivative then, and the way they like to write it is like this, 1 all over, whoops, and it's squared, right? So we don't need the square root. It'll be 1 all over 1 plus x squared. Okay. So in general, we have these new derivatives to deal with. Okay, so the derivative with respect to u of sine inverse, which I introduced last time, will be 1 all over the square root of 1 minus u squared times the derivative of u with respect to u, or you just put u prime, the derivative of the guts, basically. The derivative with respect to u of arc tan, or if you'd rather tan inverse, I'm kind of using the other notation, tan inverse of u. That'll be 1 all over 1 plus u squared times the derivative of u. And you need these memorized. Okay? Memorize. The third one, the derivative with respect to u of secant inverse of u is equal to 1 all over absolute value of u times the square root of u squared minus 1 times u prime. Okay. And if you're curious, the other derivatives are just the negatives of these. So the derivative of cosine inverse is just negative 1 all over square root of 1 minus u squared times u prime. Okay, so if you have these two memorized, the other two are pretty easy to remember. The secant inverse is always harder, so I don't bother making you memorize that thing. Okay, let's actually find some derivatives, do some derivative work using these new formulas. So, for example, g of x equals 3 arc cosine, which is the same as cosine inverse, of x over 2. So g prime of x will be 3 times negative 1 all over the square root of 1 minus x over 2 squared, and then times the derivative of x over 2, the guts. So that'll be 1/2. Okay. And then, of course, we'll clean it up a bit. So this will be negative 3 all over 2 times the square root of 1 minus x squared over 4. We hate those complex fractions, so we're going to factor out that 1/4. Let's see how that works. So I can factor out 1/4 from the inside here. That will leave me with 4 minus x squared. And then use the square root properties to extract the 1/4. So you end up with 2 times the square root of 1/4 is 1/2. So square root of 4 minus x squared. And then 2 times 1/2 is 1. So negative 3 all over 4 minus x squared. Okay. Let's get another. Just a couple more, and then we'll probably call it quits. G of x equals e to the 2x times the sine inverse of x. Okay, so we need a product rule here. G prime of x, leave e to the 2x alone, times the derivative of sine inverse. That's just 1 over the square root of 1 minus x squared. And then plus, take the derivative of e to the 2x, that's e to the 2x right back, times 2 times sine inverse of x. Okay. Not much to do with regards to cleanups. E to the 2x all over the square root of 1 minus x squared plus 2e to the 2x sine inverse x. Okay. Let's try one more. H of t equals sine of arc cosine of t. And let's see, we get, okay, so chain rule, h prime of t is cosine, the derivative of the outer part, of arc cosine of t, times the derivative of the guts, right? So that would be negative 1 all over the square root of 1 minus t squared. Cosine of arc cosine of t is just t, so that'll just be t. Those guys are kind of cancel each other out, right? It's cancellation equations. F of g of x is x. So we get t times negative 1 over the square root of 1 minus t squared. I need to clean that up, so it's just negative t all over square root of 1 minus t squared. Okay. Right, so I guess that'll do us for this section. We'll just leave it there. So you have some new formulas you're going to have to memorize for the test. And okay, I guess that's about it. Thanks for watching, and we'll see you next time.